Hello, my name is Luke and welcome to this Pytorch deep learning tutorial series. In this video, we're going over section 6, the pre-training augmentations. So in this video, we're looking at unsupervised methods to pre-train our model before we train it for classification. As per usual, all the code can be found in my GitHub repo, so you can download it from there. I'm updating it all the time, so you can download the code and follow along if you'd like. So in the previous video, we looked at using techniques like augmentation and learning rate scheduling to improve the performance of our classifier for a model where pre-trained weights potentially don't exist. So in the previous section, we looked at transfer learning, and then we said in the last video, what happens if we don't have some pre-trained weights? Well, we can use data augmentation as well as learning rate scheduling to boost the performance of our model. That's especially useful when we don't have a lot of data to train with. In this video, we're going to look at a situation where we don't have much labeled data. So for classification, for example, we don't have many images that have been labeled, cat, dog, or whatever class they are, but we maybe have a lot of images that are just unlabeled. So again, we're going to use the STL10 dataset. And I mentioned in that previous video that it only has, say, 500 images per class, so 10 classes, got 5,000 training images, which is enough to train with, but not as much as some datasets, or not as much as you'd like. But it also has, if you can see that, 100,000-ish unlabeled images. So these are just images, no class labels with them. And what we're going to look at in this video is how we can use those unlabeled images to pre-train a model and then take the labeled images with that pre-trained model and fine-tune it to be a classifier and see if we can get an improvement in performance by using this unlabeled set. So we're going to look at two pretty basic methods in this video, two unsupervised learning methods, maybe semi-supervised, depends on your definition, that hopefully give you a starting point to understand how we can define some unsupervised learning problems. So the two that we're going to look at in this video are both classification-esque problems. We're basically going to use the route of generating labels from our images or generating labels in an automated way. So what we're going to do, we're going to look at two things. The first one, we're going to look at rotating the images and then have our model predict which rotation amount or how much the image has been rotated. So we're going to get into how we do that in our data set in a moment, but let's just have a look at what I mean. So here we have images from our data set. So this includes the training images, which do have labels, but also the ones that don't have labels. For STL10, it's called the train plus unlabeled split, but we'll get to that in a moment. So we have our images, they've been rotated by some amount, and the label here is just an index that indexes a rotation array, a rotation vector, right? So each one of these labels tells you how much each of these images has been rotated, and this is the class label we're going to automatically assign basically to each of these images. So you can see we've just automatically created some labels for our images by augmenting the images in some fixed way. Like I said, we're using the STL10 dataset, and what we're going to do is basically just manipulate Pytorch's existing STL10 dataset class, but just change the getItem function. So if we look back into Pytorch's STL10 dataset here, we can see how you might create an instance of this, and we've seen it in previous videos. If you click on the source code here, you can even see the actual implementation of it. And what we're going to do is we're just going to inherit from this class, and we're just going to change the getItem function. So all the rest of it's already done for us. We're just going to change that function that returns the image and target. We don't want the original target. For the unlabeled images, there is no target, which would be the actual class, the cat, dog, car, whatever class. So you can see here, I've created my rotate STL10 dataset, inheriting from Pytorch's STL10 dataset. Every other function is going to remain the same, but we're just going to modify the getItem function. So I've got an array here, class array that just defines, or class list, that just defines a set of angles that we're going to randomly select from to rotate our image, and then the index of the array is what the classifier will predict. Okay, it's fairly straightforward. So most of this you'll see is pretty much the same as the source code, except a few of the labeling and the transforms here we don't need, but the basic functionality is the same. If you remember, get item will get an index to the data set. So there's a whole data set of images here, and the index will index one of those images in that data set. The data for STL is stored in the self.data class, data object, and I've just got that from here. You can see how they're indexing that in the source code. So that's how I found that out. That is a NumPy array that we're going to transpose just to make sure it's in the right shape of height width or class height width, and then we're going to convert that to a pill image. This is just following along again from the source code, but usually you want to convert it to a pill image so that Pytorch's transforms can operate on it. So Pytorch's transforms, a lot of them can operate on pill images as well as tensors. Some of them can only operate on pill images. So we've got a Pytorch image library pill image object here. Then we're going to actually do the rotation where we randomly select an integer from this, from 0 to 1 take the length here. So we're randomly going to select one of these angles, but we select the index, and then we use that index to index an angle. And then we're going to use Pytorch's functional transform.rotate. So this is from the transforms.functional transforms. So there's the transforms, which are the transform objects. And then Pytorch also has those transforms just as a function. So you can just call the function instead of creating a class. And that's just what I'm going to do here so that I can provide it with the angle as well as the image. So I provide it with the image, the pill image, and also the angle in degrees that I want to rotate, and that will rotate the image for me. After that, you can pass that, this will still be a pill image, pass that to your normal transforms if you want to do some normalization or maybe changes to color. You have to be careful here because the classifier is predicting the angle. You don't want any augmentations in this transform now that sort of change the rotation or flip the image in any way, right? So we don't want to include any sort of rotations or flipping in this augmentation, this set of transforms here. Okay, so then what we do is we just return the image. This will be a tensor at this point because we'll do 2 tensor, and we want to return the index of the angle we selected, right? This integer here, we can just return this as an integer, and the data loader will convert that to a tensor with all the other, the whole batch of indexes for us. So we just need to return that as an integer. Okay, once we've done this, basically all the code is identical or near identical to the previous videos. All right, so all we had to do is modify this get item function, perform this augmentation, return the index, and then we can just plug it into the rest of our code. Right, so we just create an instance of this dataset class, and we do that exactly the same as the STL10 because we've just inherited from that STL10 class. So we initialize it in the same way, but now our get item function is going to be different. Okay, and make sure we set the split to be train plus unlabeled. Train plus unlabeled here is the dataset split. So that's the training and all of the unlabeled images. And then again, we're going to create a validation split from that as well. So because we've got so many images now, if we have a look here, we can see we've got close to 100,000 training images because we've done that split with validation. And we're going to train for 30 epochs. That's going to take quite a lot longer than the previous videos when we only trained off of the training set. Luckily, however, I've already trained this for you. And so we can have a look at the results. And we can run the test again. So you can see we get about 88% accuracy. There is a bit of overfitting here. There may be some images that potentially look very similar, or it's very difficult to tell how much it's been rotated by because potentially there are images within the data set that are already sort of rotated. And so for particular objects, you might not be able to tell. So one such case that's pretty obvious to me would be if you were looking at images of cells under the microscope, where in your data set, you might have, microscope slides or pictures of the cells rotated every which way already. So if you were to then try and use this method or this technique on that data set, the classifier might not have any ability to actually tell how much it's been rotated by, because there's no unique identifying features that tell it what the orientation should be. Something like this plane image here, it's pretty obvious. We've got the plane orientated in the right direction. We've got the ground at the bottom. We've got the sky up the top, right? So that we know when we see the tail of the plane here, we can see the sky's over here now, and the ground's over here. So we can tell it's been rotated by some amount. The same with, this truck, the ground's now over here and the sky's over here. So we can tell it's been rotated. This dog, the legs are facing up in the air, right? And that's not normal. So we can sort of work out what the orientation is there. What I'm saying is for certain data sets where you can't work out the orientation because maybe the images are always rotated normally, then this sort of technique might not be useful. But even within an individual data set, that might be the case for certain types of objects. Okay, in any case, what we can do now is we've got this pre-trained model. We can take this and use it as the starting point to train our classifier. So if we go back to the notebook we used in the previous video called Augmentations and Learning Rate Solutions, you'll see that there's this extra bit of code here, this part here that's normally commented out. If we can uncomment that, making sure that this name here is the same as the name that we set up here. So we should have a save of this model, making sure that that name is the same here. What we're going to do is basically create another model I'll create this model trainer, and we're going to start from checkpoint, and we're going to use the checkpoint that we saved. And then we're going to take a deep copy. We're going to take a memory copy. Note that I'm also loading this into CPU, so I'm not loading it into memory. Once I've done this deep copy, you could delete this model, but I'm not bothering. Once we take a copy of this, we're then going to pass it into our second model trainer. Right, there are other ways you could do this, but this is just how I've sort of cut and pasted this together. And then we're going to use this model as the starting point to train our classifier. So once you've just uncommented this part, assuming the names are all correct, making sure your output size is correct. So we've got 7 output size, 1 for each of the angles, 0, 1, 1, 2, 3, 4, 5, 6, 7. That's correct. We're going to then train from here. Okay, so once we've done that, we're just going to change this. Rotate. So rotate pre-trained. Just a reminder, these are from the previous videos and accuracy. What I'm going to do is I'm going to train with all of the augmentations as well as that cosine linear, and we're going to train for 60 epochs. So we're looking to beat about 69.62% accuracy on the test set. So I'll click run all and we'll get back when that's done. Right, training's over, and you can see we've got a 71% validation accuracy, so it's a good sign. If we scroll down, we can see, yes, our unaugmented test accuracy is 75.2%. So we've got about 6% improvement in accuracy. So what we've effectively done is created our own pre-trained weights, then use transfer learning to copy that and train our own model. So just a reminder, we're using just the default STL10 dataset with the training split, same as before. So the only thing that has changed is we're using the model we trained with the rotation augmentations as the starting point. You can see it's not quite as high as the transfer learning where we took the model trained on ImageNet, but we've definitely got an improvement. Again, we're assuming that we potentially don't have any pre-trained weights and we want to make our own. But as I said, that technique of the rotations is not potentially applicable to a lot of data sets. And so we have the second method here. So I've just duplicated that notebook and run it as well. So the second method is called shuffling or puzzle solving, kind of depends, got some different names. What we're doing here is, instead of rotating the image, we've effectively created a little puzzle for our model to solve. We've divided up our image, in this case, into a 3x3 grid, and then we're shuffling around the pieces. And then our model has to guess what order did we shuffle those pieces around in. If we go to the actual data set here, called shuffle STL10, again, all we've really done is augmented the get item function. What we're doing here first is we're actually creating or working out the number of permutations, so the number of ways we can shuffle those pieces. Unfortunately, because the number of permutations scales quite quickly, anything larger than a puzzle size of 2, so a 2x2 grid, will get us thousands, hundreds of thousands, millions of different permutations. So I didn't want to use a 2x2, so we're going to go with a 3x3, but we're only going to take the max 100 permutations, right? And that's going to be in order, so it's not going to be a huge or a good sample of them, but we're going to take the max of the first 100 permutations. And we're going to use the itertools.permutations for this input array to get those permutations. So the easiest way I can try and show you what we've got here is if I go to my training data and I put out these permutations. Dot data set, because we've used the random split here to generate this training data. It's actually dataset train data dot dataset all perms. So here's all the permutations that we can do. So there's 9 pieces in our puzzle, and here's basically all the orders. So the first one is obviously them in the normal order, and then you can see we've swapped the last 2 around, and these are all the permutations we're going to use. For a 2x2, we could get all of them. I think there's only 24 for a 2x2, but for more than that, it scales very, very quickly to well over, I think, 300,000 or something for a 3x3. So we're just going to take the first 10 permutations. And again, this is just the order in which those tiles sit in. So it starts at 0, 1, 2, 3, 4, 5, 6, 7, 8 in order there. And then this is the new order that those pieces are going to be in. Hopefully that makes sense. And the reason we've done it like this is, again, our model is not going to predict the order. It's going to choose from that list which one of the shuffling permutations it thinks has been performed on the original image. The way I'm doing the shuffling is using Pytorch's pixel shuffle and unshuffle. I'm not going to go into too much detail on this now. It's not usually used in this context. It's usually used as a layer type within a model, but it's quite useful actually in this context. Basically, we're going to use this to shuffle and unshuffle our image and do the permutations. The actual way I've done this is probably not the best way, but it does work. But what is important is showing you how we can create these sort of augmentations. And then what we're essentially doing here is predicting what augmentation has occurred to our image. So don't worry too much about the implementation. We'll try and focus more on the concept of what we're trying to do in these unsupervised methods. We're trying to automatically generate these augmentations, but hopefully you get an overview of what this particular one is doing. So this might be more applicable for, say, the case where we have the pictures of cell cultures, right, where the rotation might not be the best augmentation to use because the cells are always rotated or always pictured in different orientations. But in this case, we're sort of rearranging the image, and that might be more applicable for your particular data set. Again, you just have to be careful and make sure that it's actually possible for the model to actually predict what's happened to it. So again, training this takes quite a long time, takes about half an hour. We're training it for the same amount of time, but I've already pre-trained it for us. You can see it didn't overfit as much on this one, and we get about a 91.65% accuracy on the test set, which is very good. So we're going to now use this one as the starting point. All we need to do here is change the name of the model. So I've called it shuffle. And the output was 100. And we're just going to train a new model using this model now as the pre-trained weights. And we're going to do transfer learning and see how we go. All right, I'll get back when we're done. All right, so training has finished on that one. You can see 70% validation accuracy. That test accuracy is only 71%. So this pre-training method doesn't seem to have helped as much as the rotations. Again, that's going to depend on the data set. So for this particular one, may not have been as useful on the STL10 dataset for the puzzles, but the rotations were more useful. I've also created a very simple implementation of this shuffling and puzzling. In the original paper, they don't shuffle or don't take these puzzle pieces exactly by just splitting the image into a grid. They tend to take the image and leave a bit of space between the pictures. So in my case, I've done something like this and just rearranged this grid, whereas in the original paper, they've done something like this. So they haven't actually divided it straight into a grid. The squares are still all square. Ignore my bad drawing. And the reason they've done it like this, if you imagine a 3x3 grid, is because the model can kind of easily tell what the neighboring block is simply by looking at the pixels right on the edge here. So to prevent that, you might want to leave a bit of a gap in between them so it just can't cheat. So it actually has to look inside these boxes, inside the puzzle pieces, instead of just the edges. But again, hopefully you can see we did get a bit of a boost, but it's going to depend on your data set. So a few things to close with. You don't necessarily need to use your own data set for this pre-training methods. So here, we've assumed that we've got some giant data set and maybe we've only labeled some of the images and we've used the unlabeled ones to pre-train and then trained the classifier on the labeled ones. You could, however, have a small data set of images that have been labeled, and you can go out and find another data set that might be labeled for some other task. For example, you might have some X-ray images that you're trying to classify, and you can go out and find another data set of X-ray images that might be, labeled for broken bones or some other disease that you're not interested in. But because you don't need the labels for the pre-training, you can throw away those labels and just use the images themselves as the pre-training data set. And then you can fine-tune on your data set. You could also just train on the labels from those images and use transfer learning. But either or, you don't necessarily need to be too worried if your data set is too small. Using these pre-training techniques and transfer learning, you can still get a usable model that has a high enough test accuracy. Okay, so that's all I'm going to cover in this video. There's a lot of other pre-training techniques that we might get to. Let me know if you're interested, and I might make another video on this sort of topic. But that's all. Remember to like and subscribe. The GitHub repo is there for all the code if you need it, and I'll see you in the next one.